10 ਮਿੰਟ ਵੱਲ ਲੱਗੀ ਦੇਵਾਂਗੇ ਓਕੇ Bismillahirrahmanirrahim. I am just briefly going through what we learned last time. Angular momentum is a very important physical quantity in quantum mechanics, and it is defined as L is equal to R cross P. It is a similar expression which you have in classical mechanics, but there it is vector L is equal to vector R cross P, and since P and R, they have cross, they are two vectors and they have cross between them, therefore they do not commute. So in classical mechanics you can write it as minus P cross R, and it still has the same meaning of angular momentum. But in quantum mechanics, since R and P can be replaced by operator, this is a symbol to represent vector as well as operator. So you cannot write in quantum mechanics that L is equal to minus P cross R, because it will change its meaning. It is no longer angular momentum. Then with the help of determinant, we can write L as this 3 into 3 determinant, and when you find the component, you see the 3 component of this Lx, Ly and Z. Lx will be ypz minus zpy, Ly will be equal to zpx, zpx minus xpz, and Lz is xpy minus ypx. And look at the cyclic order, okay? So you have to go, when it is x, next is y. When it is x, next is y, and next is z, and then again is x. So when you say Lx, so it will be ypz minus zpy. Lx is ypz minus zpy. Ly will be equal to zpx minus xpz, and Lz will be equal to xpy minus ypx. So you have to maintain this cyclic order. Then what I have done, I have replaced Pz by its corresponding quantum mechanical operator, which is minus I h bar delta over delta z, and etc. etc. So you have 3 components. Square of this is square of this plus square of this plus square of this is equal to that thing. Now this thing we didn't do last time, that is the conversion from Cartesian coordinate to spherical polar coordinate, and from spherical polar coordinate to Cartesian coordinate. Now look, this is a vector R which is given in a space like this, okay, and it is making an angle theta with z-axis, that is z-axis, you can see in the figure. So its component here will be R cosine theta. So its component along here is R cosine theta. This component is R cosine theta, okay, and this is in fact Z. So Z is R cosine theta. Then you have its projection perpendicular to that. So that is one projection, and that is another projection, that is this one, that is R sine theta. So that is R sine theta. Then you resolve this R sine theta into 2 components, one here and one here, because R sine theta is making an angle phi. Well, what is angle phi? It is the angle made with x-axis by the projection of R in xy plane. In xy plane there is R sine theta, and it is making an angle of phi there, and therefore its component here will be R sine theta and then cosine of phi. And similarly, perpendicular to this will be R sine theta and sine phi, that is y. Okay, so y is R sine theta sine phi, x is R sine theta cosine phi, and if you use these, do some mathematical details which I will tell you in the live lecture next week, then you can transform this from Cartesian coordinate to spherical polar coordinate. So these are the three expressions of three component of angular momentum in spherical polar coordinate, and that is the scale of angular momentum in spherical polar coordinates. Okay, so look at that. These are quite different expressions than this one, because you have transformed them to spherical polar coordinate and you are not using the Cartesian coordinate. Now, in most of the cases, why we transform angular momentum in spherical polar coordinate? Because most of quantum mechanical problem are spherical symmetric problem. When we say spherical symmetric, it means that you are talking about sphere, and whether you are talking about large sphere or small sphere, what is common in them is that whether it is large sphere or small sphere, the angle theta ranges from 0 to pi. Angle phi ranges from 0 to 2 pi. And the only difference between two spheres is radius r. Now look, suppose that this is r. This is making an angle of theta with z axis. Okay, you go around there, so you will be making, when you go to the next quadrant, what you will see that it is making a semicircle. Okay, its tip is making a semicircle. If you start from r from 0 angle, and then you say this angle and that angle and that angle, 90 is here, so 1/4 of a circle is there, and when you go down there, half of the circle, and then you rotate that semicircle in this, that is an angle of phi, which ranges from 0 to 2 pi, so you will have complete circle there, sphere there. So this is why they are known as spherical polar coordinate. Okay, having done with that, then we come to the commutation relation. By what happens if you have Lx and Ly, and what happens when you have Ly and Lz, and you have Lz and Lx. Again, look at the cyclic order: x to y, y to z, z to x. Okay, cyclic order is there, and therefore it is equal to IH bar Lz, IH bar Lz, and that is equal to IH bar Lx, and that is equal to IH bar Ly. Now, if you change the order, then what will happen? Ly Lx, that will be minus IH bar Lz, and here Lz Ly is equal to minus IH bar Lx, and Lx Lz is equal to minus IH bar Ly. So, you know, if you go in the opposite direction, y to x, z to y, x to z, then you change sign there. Now look here. Two components of angular momentum do not commute with each other. Now this expression means Lx Ly, this square bracket means Lx Ly minus Ly Lx. Now if you have two general operators A and B, and you say, okay, what is A and B, then you can write it as AB minus BA. These are two operators generally. Now sometime result is 0, and sometime result is not 0. And when result is 0, A and B commute. And when this is not 0, then A and B, they do not commute. They do not commute, okay? So when AB minus BA is equal to 0, it means that the two operators, they commute with each other, and when it is not equal to 0, it means that they do not commute. Now in these components, three components, Lx, Ly, it does not commute, okay? They do not commute. Answer is I h bar Lz. Similarly, Ly, Lz, answer is I h bar Lx. Lz, Lx, answer is I h bar Ly, and you must have done this in your BS or MSc course. Okay, prove that this is equal to that, and it is given in any basic book of quantum mechanics which you study during your BS or MSc course. And this is usually given in the form of a problem. You can, look into the book and you can see the proof, how it is proved there. Okay, and you will see that is the answer which you get, that is the answer you get, that is the answer you get. But that is mathematics. Okay, that is mathematics. What is the physics of it? Again, I'll go to those two operators A and B, and when A and B commutator is equal to 0, we say A and B commute. It means that if A and B, they represent two physical quantities and result is 0, commutation is 0, it means you can measure both of them simultaneously with the same level of accuracy. There is no uncertainty in their measurement. Okay, when two operators representing physical quantities, they commute with each other, it means that you can measure them. Take that.